Today I want to talk about sediments. And remember, these cover most of the floor of the ocean, except in a few places. Sometimes they're very thin, a few centimeters. Sometimes they're quite thick, several kilometers. About the only place where you have extensive areas without sediments is at the mid-ocean ridges, where, remember, rock from the mantle of the earth is coming up, okay, and resulting in what we call seafloor spreading. Now, the investigation of sediments on the oceanic plates, remember, was an important aspect of finally substantiating that basic idea of seafloor spreading, which led then to the acceptance of the general theory of plate tectonics. Let's take a brief look at that, and we'll look at the ocean floor. Okay, well, this should be a fairly familiar diagram here. Right out here in the middle of the ocean, remember, we have the mid-ocean ridge, which we often call the MOR. And remember, the seafloor is spreading out in this direction, and it's spreading out in this direction, and eventually being subducted down back into the mantle of the Earth, remember, the next layer down. This is continental crust in this particular instance over here, okay? Rock which is largely granitic in character, and oceanic crust, rock which is largely basaltic in nature because it comes up here, as a lava that is relatively rich in iron and magnesium. Now, while this process is taking place, and remember it's a slow process, a few centimeters per year, the ocean floor is drifting out in this direction. It's also drifting out in this direction over here. Remember, this is what we call a divergent plate boundary. Well, while that is happening, sediments are constantly being deposited on the ocean floor. They're gradually falling down here. Sediments of various types are coming down off of the continent, for example. And they pile up. They get thicker and thicker as you move away from the mid-ocean ridge, because remember it's moving out. Sediments are falling on it for a longer period of time. So you have a relatively thick layer of sediment here. Now remember, this is particulate matter, fine grained, sometimes relatively coarse grained, but usually relatively fine grained material, which gradually comes down either off of the continent. It can be formed in the ocean. We'll take a look at these different aspects of it here in a moment. It can be blown in by the wind and fall down through the water. But notice that after maybe 150, 200 million years, much of it is going to be subducted. It's going to be carried back into the mantle of the Earth. Okay. Some of it may be caught here and remain without being pulled down, but in general that means that most of these sediments which accumulate, right at the top of these moving plates, is only going to represent a relatively small part of Earth history. Fortunately, however, here on the continental crust, there are areas which have been under sea level for a long time, and there we have much older layers of sediment that can pile up. So we can get a good idea, of what the sedimentary history of the Earth was from looking at some of these marine sediments, seaborne sediments, which accumulate on the edge of the continental crust over here. Now, in your textbook, the author refers, in fact, to the Grand Canyon, indicating where the Colorado River is cut down through a number of layers, some of which were deposited a long time ago, in the oceans. Probably in shallow seas, maybe at times when sea level was quite a bit higher, and you could get marine sediments in places that are now more or less high and dry. Hence, remember that sediments had a lot to do with the development of the theory of plate tectonics, because it greatly substantiated the basic idea that we have divergent plate boundaries out in the middle of the ocean, and that the ocean floor is pulling apart there. And one evidence of that is the accumulation of sediments getting thicker and thicker and thicker and older and older and older, at the bottom of the sequence of sediments as you get further and further away from the mid-ocean ridge. Well, we usually divide sediments up into 4 major categories. 2 of them make up a large proportion of the total amount of sediment. And these are what we call terrigenous, derived from the land. And remember, in the hydrologic cycle, most of the water that gets into the atmosphere is evaporated from the ocean. Okay? Some of it falls on the land. It forms streams. In some places it forms glaciers. That water, or ice, eventually comes back down to the ocean, completing the cycle, the hydrologic cycle, and along the way it carries quite a bit of solid material along with it, and these may become the sediments which pile up in the ocean. So, terrigenous sediments, those coming from terra, coming from the land. We also have biogenous sediments, those which are secreted by organisms of one type or another, biologically formed. Many organisms have, whether they are algal types or animal types, they often have hard parts, they have shells or bones. Okay? When the animal dies, these are going to sink down to the bottom of the ocean. There they often go through some interesting transformations, but this also is a very important part of the sediments of the ocean floor. Now, the bulk of the material is actually terrigenous, but most of this accumulates along the shoreline. The biogenous sediments are more extensive because they can be deposited just about anywhere. Okay. We also have some relatively smaller sources. One of these is what we call hydrogenous. Those which form out of the ocean water itself. Like a precipitate that you might get in a test tube in the chemistry laboratory. The water becomes supersaturated in some particular material, and it becomes precipitated as a hydrogenous sediment, forming right there in place, at the place in which this chemical reaction takes place. Then, again, relatively small amount, but extremely dramatic when it occurs all at once in a major event, is the cosmogenous, coming in from outer space. A very dramatic example of that is the impact from an asteroid, remember, which struck the Earth about 65 million years ago, ending, the reign of the dinosaurs, and very famous for that point of view. But also, it had enormous impact on the life in the ocean. And we will be coming back to that later in the course when we start looking at life and the history of life in the oceans. In general, from current times back for most of the intervening period, we have small amounts of material coming in from outer space. Material may come down and become melted. It forms little molten droplets. They fall into the ocean. They find their way to the bottom and accumulate as part of these other types of sediments. When we do have a major event, like that one 65 million years ago, then we can have a very large area, in which both the material itself, which came in from outer space, and the rock material that was pulverized by the impact, can cause a relatively large area of what we call cosmogenous sediments. Well, let's take a look at the terrigenous, which again, remember, is the largest volume of sediment, but it's not as widely distributed because most of it is going to be piled up at the edge of the continents. Well, much of this is going to come from streams, so let's take a brief look at a river, a stream coming in, very simplified. Here's a channel, and we'll just fill it up with water. See here? This would be the floodplain up here. When there's more than the normal amount of water in the stream, it'll rise up here, leaving deposits on either side over here. And this is somewhat analogous, remember, to what happens in the ocean. Sometimes we have a very high stand of sea level, and at that time, land that is normally continental in nature is going to become seafloor, and we can get seafloor sediments there, for example. Well, what's coming through the stream here? These are what we call the banks here, the stream. Here's the bed of the stream here. Okay, and the stream is going to be carrying material along, which, if it doesn't end up in some type of interior lake, like the Caspian Sea or the Great Salt Lake or something of that nature, eventually it's going to be coming out into the open ocean. There will be very fine-grained material being carried in suspension by the stream. Now, how big this particulate matter is going to be in terms of the dimensions of the individual particles will depend a lot on how fast the stream is flowing. If it's flowing relatively slowly, it can only carry very fine-grained material. If it's moving relatively fast, it can carry, sand or gravel-sized material. In any event, once it reaches the ocean, it usually gets deposited fairly quickly, except for the very, very fine-grained material. Okay. Well, this is what we call the suspended load. And it accounts for a great deal of the actual particulate matter that we find out in the ocean. Now, along the bottom, there's material that can't be suspended in the moving water, but which can be dragged or rolled along the bottom. Material down here. It's on the bed of the stream, so we call it the bed load. Okay. Now, some streams carry an enormous amount of material. The Huanghe River in northern China, the Yellow River is so called because it flows through an area in which there's very fine-grained deposits, which it then picks up, carries down as a very, very massive amount of suspended load, and eventually discharges it out into an enclave of the Pacific Ocean. That is called simply the Yellow Sea, again because of the color given to it by that suspended material. On the other hand, go to the Green River in Kentucky, which flows through the Mammoth Cave area, where calcium carbonate has been dissolved, creating those caverns. If you look down into the bottom, towards the bed of the Green River, it looks green because you can actually see the algae right down at the bottom there. It appears to be perfectly clear. However, it is carrying material that is not in suspension. It's not a bed load. It is a dissolved load. In other words, it's there in the form of ions, which are moving along as dissolved material. You can't see them, but there may be an enormous amount of it. So we can also have, as part of the water itself, I might say, a dissolved load also. Now, of course, this, once it gets out into the open ocean, can be, it's not going to accumulate at any particular place. It's likely to get washed all the way around out into the center of the ocean, down to the bottom of it, and so forth. So this becomes a part of the chemical characteristics of the ocean itself. Okay. Well, these are the different types of loads. The bed load usually ends up right near the shore because it's relatively heavy stuff. Okay, the suspended load can be carried further out, and the dissolved load can be distributed widely, throughout the oceans. Now, another interesting way in which sediments can be carried is by glaciers. And when a glacier comes down to the shoreline, it will break off into an iceberg. And an iceberg is not just a great big ice cube, because it will have picked up some of the continental rocks on the way, and will have that embedded in the glacier itself. So, Suppose here's our iceberg. And remember what we see is the so-called tip of the iceberg. Remember, it has a density a little bit less than that of the water, so it's floating, but most of it is going to be below sea level here. Okay. But remember, it's going to be carrying along with it masses of rock material that it has broken loose from the continent over which it has been moving. This can either be a relatively small glacier, like an alpine type glacier, or it can be an extremely large one like Antarctica. Okay. In any event, it's got material in here which is embedded in it, and when the glacier pushes this iceberg out into the water and it begins to melt, this material eventually is going to sink down to the bottom. So we're going to have glacially derived terrigenous sediment. And this can be carried during an ice age when there's a great deal of ice on the land and a great number of icebergs breaking loose and drifting out into the oceans. This material can be carried thousands of miles away from the coast. And in addition, they give us a pretty good record of what was going on during that ice age. And we'll get back to this later on in the second half of the course. We'll be looking at the expansion and contraction of the ice, over the last 3 million years. And these glacially derived sediments on the ocean floor give us a very good record, of what happened during that period. We can even go back before that, many millions of years ago when we had previous ice ages, and we can learn quite a bit about them from these same types of deposits which we find on the ocean floor. So this is extremely important, not only from the point of view of the total amount of material that is carried out and that piles up on the ocean floor here, but also what it tells us about the past. Okay. And remember, a lot of this information that we are trying to put together about the Earth is derived not just from the land, not just from the ocean, but from both. And a great deal of it is terrigenous type of sediment which comes down from the land, eventually either by streams, by glaciers, or simply by the wind. Remember, the wind can be carrying fine-grained material which can come all the way across the oceans. For example, we have found that dust from the Sahara Desert in Africa has ended up, in South America. Well, of course, on the way, it had to cross over the Atlantic Ocean, so a large part of that, would have fallen down into the Atlantic Ocean, and we can find it there. Okay. One other source of terrigenous sediments that is very important, especially during episodes of extreme volcanic activity, is simply volcanoes. When a volcano emits a lot of ash and dust and cinders and so forth, that material, if it occurs, on a land volcano, most of it will end up on the land. However, many volcanoes, remember, are on islands in the ocean, those volcanic island arcs, or volcanoes like Hawaii. And a lot of this material then is also going to end up on the ocean floor. It comes from the land, so it is also terrigenous sediment. And again, this helps us a lot in understanding quite a bit about the history of the Earth. And we'll come back to it later on in the course. Thank you.